Right. Okay, children. Good evening, all of you. This is errors finding notes, Nana. After completion of every mains model and advanced model examination, you need to write solutions for the questions which you left in the examination and which you did mistakes in the examination. Nana. It is called errors finding notes. Here, this is a mains model examination, September 5th, Nana. Here, the solutions for the chemistry part. Question number 26. Here, the IUPAC name of the compound, Nana. This is the compound. Here, 1, 2, 3, 4, 5, 6, 7, 8. Numbering from left to right or right to left. Both give same answer, Nana. Here, 2. Second position has double bond. 2. Z configuration, Nana. Here, both hydrogens on same side. Here, both heavier groups on same side, Nana. So, 2Z. Here, 4E. 6Z, Nana. Octa 246 triene. That is IUPAC name of the compound. Second position has double bond, fourth position has double bond, sixth position has double bond. Here Z configuration, E configuration, Z configuration. This is a trans, this is cis, Nana. 27th one. Here number of geometrical isomers of the given compound. This is the compound, Nana. Here 1, 2, 3, 4 double bonds are there. Here this is not the geometrical center, Nana, because here 2 hydrogens are attached to the double bonded carbon. This double bond restricted rotation system does not show geometrical isomerism. Here it will show the geometrical isomerism. It will show the geometrical isomerism. Again, this double bond will not show the geometrical isomerism, because for this double bonded system, here in both directions we get the same groups. And here ring also does not exhibit geometrical isomerism, because cycloalkanes with sp3 carbons can exhibit, Nana. So these two double bonds exhibit geometrical isomerism. Total number of geometrical isomers 2 to the power n for unsymmetrical polyene, Nana. So 2 to the power 2, you get 4 geometrical isomers. 28, which will not show geometrical isomerism. Here geometrical isomerism conditions, Nana. Once check the conditions. Here 2 methyl groups are attached to the restricted rotation system, NOH. This is a ketoxime. We already discussed this. This is a symmetrical ketoxime, Nana. In aldoxymes, formaldehyde do not show geometrical isomerism. In ketoxymes, symmetrical ketoxymes will not show, Nana, because that is the condition, Nana. Here 2 methyl groups attached to the double bonded carbon. So restricted rotation is the condition, and planarity is another condition, and double bonded groups attached to 2 different groups, Nana. 2 different groups attached to the double bonded system, and aerial distance. These are the conditions. So it violates one condition. So it does not show geometrical isomerism. Question number 29, Nana. Here cyclopropyl ring with 3 different cyclopropyl rings, Nana. Here this molecule show how many geometrical isomers. If you observe the cases, Nana, here 3 groups, 3 cyclopropyl rings on same plane, and 2 above the plane, another one is below the plane. Next 2 below the plane, 1 above the plane. One more possibility, 3 below the plane. These are the possibilities here with respect to these two, cis, 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 trans, trans, cis, cis, trans, trans, nana. Opposite plane, trans, opposite plane, trans, same plane, cis. Here all are same plane, nana. All together cis. So here you get these two are same compounds and these two are same compounds. Nana. Look at this, trans, trans, cis, trans, trans, cis. These two compounds are same and these two compounds are same. Total possibilities here two geometrical isomers. Two geometrical isomers are possible for this compound. Okay. Next question, Nana. Question number 30. Here, which is a diode system, Nana. In tautomerism, we have two different types: diode system and triode system. Diode system means hydrogen oscillation taken place between two atoms. Nana. Here, hydrogen attached to this. Here, this is second one. First atom, second atom. Hydrogen oscillated from carbon to nitrogen. Nana. Here, hydrogen, nitrogen. Nana. This is a cyanide. This is isocyanide. Hydrogen oscillation taken place from carbon to nitrogen. That's why this is a diode system. In remaining all cases, we get triode systems. Question number 31. C3H9N. Here number of primary, secondary, tertiary amines. Nana. Here this is a amine general formula. Nana. You get different types of amines. Look at this. These are the possibilities. Nana. 1, 2, 3, 4 compounds. Nana. 4 structures. All are amines. These two are primary amines. This is a secondary amine. This is a tertiary amine. Nana. NH2 group primary, NH2 group primary, NH group secondary, N with 3 different alkyl groups. That is a tertiary. So 2 primary amines, 1 secondary amine, 1 tertiary amine. Question number 32. Look at this. Here two different structures of cyclohexyl ring. Nana. Here look at this. Here this oxygen attached with the cyclohexyl ring. Here this oxygen attached with the phenyl ring. Nana. These two comes under what? Metamers. Nana. Metamers. Here this is a bivalent functional group. Bivalent functional groups. Difference in the alkyl groups. Attachment of the alkyl groups. That is called metamerism. The compounds are called metamers. Question number 33. Here half-life, T half is given as 69.3 seconds for first order reaction. Anna. Here we need to calculate K1, Anna, rate constant for first order reaction. That is what? 0.693 by T half. 0.693 by T half value is given as 69.3. You get 0.01 second inverse. 0.01 second inverse, Nana. This is the expression for the T half and K1 for first order reaction. Question number 34, Nana. Here first order reaction T half value, Nana. Here T half is equal to 0.693 by K1, Nana. For first order reaction. First order reaction, Nana. So here T half and A initial concentration, Nana. Here independent, Nana. Independent. Why? What is the reason? T half expression is 0.693 by K1. In this formula, there is no A term, Nana. That's why T half is independent of A initial concentration. So T half is independent. It does not depends upon A. Next one, here a relation between here look at this here BrO3 minus plus 5Br minus gives rise to 3Br2 plus 3H2, Nana. With respect to Br and Br2, here they gave the relation, Nana. Okay, rate of disappearance of Br minus, Nana. Okay, that is the relation. Write down the rate expression, Nana. First, rate expression is equal to here with respect to BrO3 minus d of BrO3 minus by dt is equal to minus by 5 d of Br minus by dt is equal to plus 1 by 3 dBr2 by dt is equal to plus 1 by 3 d of H2O by dt, Nana. This is a rate expression, Nana. Here relation between these two. Look at that, minus dBr minus by dt is equal to, here only this term means what? This is rate of disappearance of Br minus. Rate of disappearance of Br minus means here this 5 come to RHS, you get plus 5 by 3 dBr2 by dt. This is the correct relation, Nana. Plus 5 by 3 dBr by Br2 by dt, that is the fourth option, Nana. Check it. Okay, now first write down the rate expression and identify the question, Nana, which you have to relate Br minus to rate of disappearance of Br minus and rate of appearance of Br2. That's it. Question number 36 here, graphical representation, Nana. Reaction coordinate to potential energy. Graphical representation is given, Nana. Here this is a reactant, this is a product, Nana. Here this value is given as a C, Nana. And here this is ET, threshold energy or energy barrier, Nana. Here this value is given as A, means A is activation energy. Here this is delta H value, Nana. Delta H, reaction enthalpy, energy of products minus energy of reactants, or energy of the activation energy of forward reaction minus activation energy of backward reaction. That also gives delta H value, reaction enthalpy. Question number 37. Here K1 expressions, rate constant expressions, K1 value at two different temperatures are given, 10 to the power 16 into e to the power minus 2000 by t, and K2 is given as 10 to the power 15 into e to the power minus 1000 by t. And one more relation is given here, K1 is equal to K2. This relation is given in the question, check it. The temperature at which K1 and K2, K1 is equal to K2 is given. Equate both, 10 to the power 16 into e to the power minus 2000 by t is equal to 10 to the power 15 e to the power minus 1000 by t. 10 to the power 15, 10 to the power 16, you get a 10 is equal to, if this exponential form come to RHS, e to the power plus 1000 by t, actually minus 1000 by t divided by e to the power minus 2000 by t. If it come to numerator, plus 2000 minus 1000 plus 2000, you get 1000. From this, apply log on both sides, natural log and then log base 10. Log base means 2.303, log base 10, 10 is equal to 1000 by t. Here log base 10, 10 value 1. Here this 2.303 come to denominator and t come to numerator, cross multiplication. Temperature is equal to 1000 by 2.303 kelvins. Okay, now here first equate both. Here cancellation of 10 to the power values, here e to the power values on same side. Applying of log base 10, first you should apply ln natural log, then ln base 10, means log base 10. Question number 38, here units of zero order reaction, units of zero order. General Kn expression, Kn units, moles to the power 1 minus n, liters to the power n minus 1, second inverse. Here zero order means n is equal to 0. If you substitute n is equal to 0 in this formula, here K naught units, moles to the power 1 minus 0, 1, liters to the power 0 minus 1, minus 1, here second inverse. So moles per liter per second inverse. First option, here 39th one, here just now we discussed, here activation energy is equal to threshold energy minus energy of reactants. Threshold energy, overall energy. Here if you observe the graphical representation, here this is the reactant molecule, this is the threshold energy. Reactant molecules required minimum amount of energy to overcome the energy barrier. Here reactant molecule present at this point, if come to product, if it converted to product means it should overcome the energy barrier. So this much amount of energy is required. This is called activation energy. Here up to here, this is a threshold energy. Already reactant molecule present here, it overcome the energy barrier. So it required how much? This much amount of energy. This energy is called activation energy. Okay, na? So threshold energy minus energy of reactant molecules, that is called activation energy. Question number 40, here overall order, overall order 0.5. Here look at the expression, rate is equal to K into Cx to the power 0.5, sorry 1.5, 1.5 into Cy to the power minus 1, Cz to the power 0. Look at this order is what? Sum of the powers of the concentration terms involved in the rate expression. Here sum of the powers, 1.5 minus 1 plus 0, then you get 0.5. Okay, overall order 0. With respect to x, order 1.5. With respect to y, order minus 1, negative order. With respect to z, 0 order. But overall order is what? 1.5 minus 1 plus 0. 0.5 is the overall order. Question number 41. That is a rate expression. Here N2 plus 3H2 gives rise to 2NH3. Here rate of appearance of ammonia given. That is given as 2 into 10 to the power minus 4 moles per liter per second inverse. The question is what? Disappearance minus delta H2 by dt, delta T. Rate of formation of ammonia, rate of disappearance of hydrogen. This is given, and this is we have to identify. First, write down the rate expression for this. Rate is equal to minus d of N2 by dt is equal to minus 1 by 3 d of H2 by dt is equal to plus d of plus 1 by 2 plus 1 by 2 d of NH3 by dt. Rate expression. Here relation between these two look at this. Here delta NH3 by delta T value is given. Delta H2 by delta T you have to identify. Okay. Then from these two, what is the relation? Delta minus d of H2 by Tt is equal to here 3 by 2 plus d 3 by 2 d of N2 by dt. Here this is given as plus 3 by 2 2 into 10 to the power minus 4. This is a value. Plus d of N2 by NH3 by NH3 by dt is 2 into 10 to the power minus 4. Here 2 cancel, here final value 3 into 10 to the power minus 4. Once again look at this. Here this is the equation for this rate expression. D of N2 by dt plus minus 1 by 3 d of H2 by dt plus d of NH3 by dt. Formation of rate of formation of ammonia given. Rate of disappearance of consumption of H2. Rate of consumption of H2 is equal to 3 by 2 times of rate of formation of NH3. That is the value 2 into 10 to the power minus 4 into 3 by 2. 2 cancel here. 3 into 10 to the power minus 4. Question number 42. Here Arrhenius equation log k is equal to log a minus ea by 2.303 r into 1 by t. Here this is on y axis, this is on x axis. You get y is equal to minus mx plus c. Here this is angle, obtuse angle more than 90. This is x axis, this is y axis. Here 1 by t on x axis, log k on y axis. Then you get this type of curve. Y is equal to minus mx plus c. Y is equal to minus mx plus c. From this, here negative slope. Here this is the value slope. Ea by 2.303 r value slope. That's why from this you get activation energy. The next one here 2a plus 2b gives rise to c plus d. Here with respect to a, order 1. With respect to b, order 1. Means for this rate expression, rate is equal to K2 into concentration of A to the power 1, B to the power 1, second order reaction. And here 50% of reaction completed. means here the concentration, this is equation 1 nana. Here rate, this is 1, this is 2, second one nana, second case, or this is a case 1, this is a case 2. Rate is equal to K2 into concentration of A by 2 to the power 1, concentration of B by 2 to the power 1 nana. Okay na, because 50% of the reaction completed, so concentration should be half, concentration should be half. That is equal to K2 into concentration of A to the power 1 by 2 and concentration of B to the power 1 by 2. That is equal to K2 into concentration of A to the power 1, B to the power 1 by 4. Here K2, here this value nana, look at this numerator value nana, K2 into concentration of A to the power 1 and B to the power 1 is nothing but R1 nana. This is R2. So R2 is equal to R1 by 4. R1 by 4. Here R1 value is given as 4 into 10 to the power minus 2 divided by 4, that is equal to 1 into 10 to the power minus 2 moles per liter per second. Case 1 general order rate with respect to AB orders, we can write rate expression. Here after 50% of the reaction completion, here A become A by 2, B become B by 2. We can relate R1 R2 expressions now. R2 is equal to R1 by 4, R1 value given in the question divided by 4 now. Question number 44. Here ester hydrolysis CH3COO C2H5 plus NaOH gives rise to CH3COO Na plus C2H5OH. This is a base hydrolysis. Here order is 2 and molecularity also 2. Bimolecular second order reaction. If it is ester hydrolysis in the presence of acid, that is first order second molecularity, bimolecularity. Molecularity to order 1 if it is acidic medium. Here this is basic medium, order to molecularity 2. Question number 45, Arrhenius equation, K is equal to A into e to the power minus EA by RT. Here K versus T, you get exponential graph. Exponential graph means this is the graph. K, here this is T, e to the power, e to the power, exponential graph. Question number 46, here C7H7Cl. Here benzenoid aromatic structures. Look at the structures, possible structures. Benzyl chloride, orthochlorotoluene, metachlorotoluene, parachlorotoluene. These are the 4 possibilities. Benzyl chloride, orthochlorotoluene, metachlorotoluene, parachlorotoluene. 1 2 ortho, 1 3 meta, 1 4 para. Integer value 4. Question number 47. Here identification of Z isomer. Z isomer means same priorities on same side of the restricted rotation. Look at the structures. Look at this, Nana. Here first carbon. Here first carbon. Then carbon has two carbon atoms. Here two carbon atoms. But here this is a double bonded carbon, Nana. Double bonded carbon. This is first priority. This is second priority. Here first priority, second priority, Nana. Double bonded carbon. Here two, three carbon atoms. Here two, three carbon atoms. Next two hydrogen atoms. Here next two carbon atoms. That's why first priority. Here second one, Nana. Here sulfur atoms. Oxygen atom. Here first priority, second priority. Here sulfur more atomic mass or more atomic number. Oxygen second less atomic number. First priority is first priority. Second priority is here both are Z isomers. Next third compound, Nana. CH2, CH2, CH3. Here CH3, CH3. Nana. This is a propyl, this is isopropyl. So isopropyl first priority because first carbon has two carbons and one hydrogen. Here first carbon attached with two hydrogens and one carbon. So this is a second priority. Here this side CH2, CH3, ethyl group, and here cyclobutyl group. Nana. Here first carbon with two hydrogens, here first carbon with two carbons. So here first priority, second priority. Again Z isomer. Here pH phenyl group, here chlorine. Look at this. Here chlorine, here pH means phenyl Nana. Phenyl means benzene. Nana. Here this is the carbon, this is the chlorine. So here first priority, second priority. Here first carbon, first carbon. Here second carbon has double bond, second carbon has double bond. Here hydrogen atom, here carbon atom. So here first priority, second priority, again Z isomer. So 1, 2, 3, 4. All are Z isomers, Nana. Integer value 4. Question number 48. Here NH2 C double bond O, NH2. NH2 C double bond S, NH2. Here benzene ring with OH and NO. Okay, na? Then acetone, Nana. CH3 C double bond O, CH3. Once check the conditions, Nana. Here all the molecules exhibit tautomerism, Nana. Tautomerism structural condition, two conditions. Electronegative element with multiple bond, electronegative with multiple bond, electronegative with multiple bond. Here electronegative with multiple bond. And alpha carbon has hydrogen. Alpha carbon has hydrogen. Here alpha position hydrogen. And here double bond with OH, Nana. So here also geometry tautomerism observed, Nana. So here all the molecules exhibit tautomerism. 4 compounds exhibit tautomerism. Question number 49. Here for zero order reaction, Nana. Zero order reaction, T 75% is equal to 3/2 times of T 50%, Nana. Here this is given as X, Nana. X is equal to 3/2. That is nothing but 1.5, Nana. Integer value 1.5. Question number 50. Here cyclopentane, Nana. C5H10. Cyclopentane. Look at the possible structures. Here cyclopentane, methyl cyclopentane, ethyl cyclopropane, dimethyl cyclopropane. Here also dimethyl, Anna. Here 1,2 dimethyl, 1,1 dimethyl. So here 1, 2, 3, 4, 5 possibilities are there, Nana. Question number 50, integer value 5, Nana. C5H10 number of possible cyclic isomers. 5 possibilities. Cyclopentane, methyl cyclobutane, ethyl cyclopropane, 1,2 dimethyl cyclopropane, 1,1 dimethyl cyclopropane. These are the possibilities for C5H10. Okay, thank you.